This is Bill Farmer. Welcome back to McMaster University course Computing and Software 701, Logic and Discrete Mathematics. We're going to finish up today the topic of basic mathematical concepts. I'd like to talk to you first about a theorem, a fixed point theorem called the Knaster-Tarski fixed point theorem. In this theorem, we have a complete lattice and we have a function which is monotone. I'll remind you, monotone means that if A is less than or equal to B, that will imply that f of A is less than f of B. So monotone functions preserve order. So if we have any complete lattice, any monotone function that's on this lattice, then there exists a fixed point of f. That means when we apply f to the fixed point, we get back that value. So that's the theorem, and there's really a stronger aspect to it, that if we take all the fixed points of f, those fixed points form a complete lattice. Now, I want to mention that there are several other fixed point theorems related to the Knaster-Tarski theorem, and fixed point theorems in general are very useful and important in computing. So what I'm going to do now is to describe a mathematical structure that captures the idea of a directed graph. So this structure will have a set of vertices, a set of edges, those will be the domains of the structure, and then it has two functions which map edges to vertices. And the idea is alpha maps an edge to its starting vertex and beta maps it to its ending vertex. So for any edge, that edge you can say connects this vertex to that vertex. Now, if we draw a picture of this, we can have some vertices here. These will be the vertices, wherever they may be. And then we can have edges, and the edges graphically go from one vertex to another, or it may go back to itself. And we could have situations like this. So notice here we have two edges going from this vertex to that vertex. Okay, so this is what a directed graph looks like. If we go back to here, we can say a directed graph is simple if for any two members of V, there's going to be at least one member of E that connects these two. So if we go back to our simple little example here, this is not simple. It's not simple because of what's happening right here. We have two edges that are going both from this vertex to that vertex. Okay, so that's what a simple graph is, and a simple directed graph. And usually those are the kind of graphs we're interested in. There's another way of thinking about graphs, and that is that thinking about them as not being directed. So here we just have vertices, and we connect them however we want. We can even connect them like this. Now, notice there's no direction here. Now we could represent this as a directed graph. I have the same situation here, but I can make all these edges directed. But then what I will do is I will assume that we have edges going the other way as well for every possible edge. And so forth. So if we assume for every vertex, if there is an edge this way directed, there will always be an edge this way. We can call that, and then think of this as, we can write it like this. So if we have this structure of a directed graph, we can think of as particular directed graphs are undirected. So that's the definition here. Basically, an undirected graph can be represented as a directed graph such that for all edges there is another edge that goes in the reverse direction of that edge. Now this way of defining directed graphs, this way of defining this structure, is one of many ways you can define graphs as mathematical structures. Now one important aspect of a graph is connectedness. And if we have a graph where we have several vertices, we can imagine, and let's say they're connected like this. We can talk about a path. And basically a path is, if we start with, let's say this node, this would be, let's see, I'll call that U0. This is U1, U2, U3, and then we're back here to U4. So we can think of that sequence of U0 up to U, actually let's call this, well this is U4, but they're U1 and U4 are the same. This sequence is a path. And if we have a graph, we can say that two vertices are connected if there's a path between them. And we can say the whole graph is connected if there's a path between any two vertices. And then a cycle will be a path like this path, where we start at U2 and we get back to U4, but U4 and we start at U0 and we get back to U4, but U0 and U4 are the same vertex. And we'd say G is cyclic if there is some cycle in G. So these are important notions. And the last thing we're going to talk about is a very special kind of directed graph, which is a directed tree. And a directed tree is a directed graph where we have a root, some special node called the root, and from there we have edges going to other places. We can have lots of these. And so from this root, there is a unique path to every vertex. Now what this means is, so this actually implies, you can see right away, it implies that it's going to be simple. If it weren't simple, we'd have two paths. If we have this showing it weren't simple, we could go this way or this way to get to here. So the unique path part makes sure that it's simple. Let me get rid of this part. It makes sure it's simple, and the other thing it implies is that it's acyclic. Because let's say we had a cycle here, then we could have a path that goes from here to here to get, let's say this is X. We could go from the root to X this way, or we could go to X, to here, back to X, maybe several times. So there'd be several paths to X. There would not be a unique path. So a directed tree is always simple. It's always acyclic according to my definition. So I want to emphasize that there are many ways of formalizing graphs. This is just one way. It works pretty well. We can talk about the basic notions. Okay, so this ends our series of lectures on basic mathematical concepts. Thank you very much. Goodbye.